to the y of the exponential function, e to the x, this is e to the x, is being defined by 1 plus x plus a half x squared plus a 6x cubed, and so on. Okay. I've got a function. Now its property. And the key property is this one. Can I move to the next board? So the next step is check. Well, I've asked you. I've got e to the x. And let me write again what it is. 1 plus x plus a half x squared plus 6x cubed, and so on. And then I've got e to the any other power, or even the same power. 1 plus, I'll just use capital X for this power. 1/6 of capital X cubed plus so on. And I want to multiply those and see what I get. Okay, I apologize. Here I ask you to believe in this infinite series. And, you know, a little dodgy, but it works. And now I ask you to multiply two of the things. You may say, okay, you're asking a lot here, but go, just hang on. Let's multiply these. E to the x times e to the capital X. Because that's what I'm interested in knowing. Okay, can you just do all the multiplications? So, and we'll see what we get. Okay, so 1 times 1 is 1, no problem. 1 times x is the x. 1 times this x is the big X. Now, can I keep going? All right. Well, 1 times a half x squared is, and now I have a x times a big X. And now I have a 1 times a half big X squared. And more, of course. Notice the way I'm doing it is like I'm keeping all the things that have 2 x's together. And then I would keep all the things that have 3 x's together, and so on. Now, what is it that I'm hoping? I'm hoping that this is the same as the series for x plus capital X. Okay, what's that? That's my exponential series, and every time I have to put in x plus capital X. In other words, of course, it starts with 1, and then it has the x plus capital X, and then it has the 1/2 of x plus capital X squared, and it keeps going. And I just want you to say yes. I guess I hope you say yes when I ask, is this big multiplication the same as this one? Well, I think it is. Let's start the check anyway. The 1s are good, the x and the x. I'm really just putting parentheses around all the, now I'm going to put parentheses around all the second degree terms and say, is that the same as that? Yeah, this is the critical point here. Do we at least start out correctly? So you have to remember how do you do, but of course you do remember how to multiply x plus capital X by itself. You just do the multiplications. X, when I multiply that by itself, I get x squared with a half, I get that. And then you remember how many x times x's do I get? Little x times big X, there would be 2 of those. But then the 1/2 factor leaves me with 1, and that's what I want. And then finally, this guy by himself, squared, is the 1/2 capital X squared that I also want. So far, so good. Do you want to see the cube terms? I don't, well, I'd rather you did it, but I should at least show that I'm willing to try. So what do I mean by the cube terms? I mean that here I want to get the next one should be 1/6 of x plus x cubed. And from the multiplication, I get some separate pieces. I get 1 times this, I get a 6. When I do that multiplication, I get 1/6 x cubed. And then I maybe get some 1/2 x squared times x. Oh, you see why I would rather you did this. But I'll finish this little line. There's also a 1/2, an x times 1/2 x squared, so that's a half of x times the big X squared. And then there is the 1 times the 1/6 x cubed. So those are the 4 pieces that come, third degree, when I do the big multiplication, and they have to match the third degree term in the last line. And they do match. If we cube thing, do you remember the right words to say now? Binomial theorem. The binomial theorem tells you how to take the nth power of a sum, like x plus capital X, to the nth power. It tells you all the many pieces you get, and those many pieces are exactly the pieces that we get directly by multiplying that line by that line. So the binomial theorem at long last pays off and confirms our great property here. So this is a big deal. Okay. So let me now come back here, having checked that. I wanted to say something about this series. 1 plus x plus a half x squared, where the typical term is x to the nth over n factorial. This is the, I would say, the second most important infinite series in mathematics, the exponential series. And it's the way I wanted to construct e to the x by matching term by term and seeing that these n factorials show up. You might want to know, what's the most important series? Reasonable question. For me, the most important series would be the one looking like this, except it doesn't have the fractions. For me, the most important series would be the one, I'll slip it up here, 1 plus x squared without the half, plus x cubed without the 1/6, plus so on, plus x to the n without this n factorial that's making it so small. Can you see this? 1 plus x squared plus x cubed plus x to the n? That, I think it's called the geometric series, powers of x. Now, it's simpler because it doesn't have these fractions. But it's riskier because those fractions were making the exponential series succeed. Whereas here, with the geometric series, well, look what happens when x is 1. When x is 1, we have 1 plus 1 plus 1 plus 1 plus 1, forever all ones, it blows up. And when x is bigger than 1, that series blows up even faster. So this series, the geometric series, this most important one, does succeed, but only for x, only when x is below 1. X equal 1 is the cutoff, and it fails after that. There is no cutoff for the exponential series because of these dividing by these bigger and bigger numbers, this works for all x. Okay, so those are the two series. Okay. Now, what happens, so let me ask you, what happens if I put x equal 1 in the exponential series? That gives me e to the first power, which is e. So finally, you may say, this is rather late in the day, I'm going to figure out what e is from this series. Put in, set x equal 1, and you learn that e to the first power, which is e, is, can I just put it in? 1 plus, x is 1 plus 1/2 of 1 squared plus 1/6 of 1 cubed. What's the next term in this? So these are numbers now, and I'm getting a number. I'm getting this incredible number e, named after Euler. Euler was a fantastic mathematician. I think he wrote more important papers than any mathematician in history. So he was allowed to name this number after himself, e. E-U-L-E-R, his name is spelled. Okay, what's the next term? This is 3 factorial, right? 3 times 2 times 1. The next term will be 4 factorial. I'll multiply that by 4. It'll be a 24th. And then times 5, 120th. And so on. They're getting small. What can I tell you about this number? It will be a definite number. It's more than, well, it's certainly more than 2.5, because I start with 2.5 here, and then I add these. Well, I could even throw in 1/6. It's more than 2 2/3, would that be? If I quit here, I'd have 2 2/3, and then I get a little more. It's easy to show. No way you would reach as far as 3. These later terms are dropping too fast. And actually, the number turns out to be, so it's 2 point something, let's see, a little more than 2 2/3. So it's around 2.7. But it's not exactly 2.7. In fact, it's not exactly any fraction or any finite decimal. It goes on and on. 1, 8, 2, 8, something. I think there are like more 8s than you'd expect right here at the beginning, but then in the long run, not. In the long run, yeah, so that's the number e. Okay. Oh, so now we know e. We know e to the x, we know e, we know this.